Hello and welcome back. So I'll continue my discussion of probability distribution functions. So in the earlier part of this class or in the previous lecture, we saw that how to generate empirical distribution or an empirical cumulative distribution function for a continuous variable using plotting positions. And in this class, we're going to talk about some common probability distribution functions or some of the theoretical models for assigning probabilities or for modeling random variables or the probability distribution of random variables. So learning objectives, we want to look at some common probability distribution functions, understand the differences between discrete and continuous probability models. And as we do this, I want to illustrate where probability models can be useful in hydrology. Again, my goal here in this class is not to show you how to get the parameters for the probability distribution function. We're going to do that in the next lecture, but to kind of give you a broad overview of what these models look like and what are their potential uses in hydrology. So just to recap the probability models, we have the probability density function and the cumulative probability distribution function. The PDF measures the likelihood of a random variable to take a given value. So if you look at the PDF plot here, what it says is that X has a good chance. There is a greater likelihood of us seeing X more so than seeing a value of -3 or +3 for that X. Okay, so this is the probability density. This is not the probability. And if I integrate under this curve, I'm going to get the sum of all probabilities, which is equal to 1. Okay, so the area under the PDF is always 1. In discrete distributions, we call the probability density function as the probability mass function, and I'll get to that in a little while. The other model for probability is the cumulative distribution function. CDF is a function whose value represents the probability that's less than or equal to some argument. So if I say what is the probability that my random variable X is going to take a value less than or equal to 0, then this big X or the capital X is 0, and I want to find out the probability of X being less than or equal to 0. So I go on to the chart and say that that's about 50%. Okay. The highest value of CDF is always equal to 1, and the lowest value of CDF is always equal to 0. So my y-axis always will be between 0 and 1, and depending on what values your X can take, the x-axis can vary both through positive and negative. Really, the cumulative distribution function is what we'll be using in hydrologic analysis for the most part. In case of discrete variables, we can sometimes use probability mass function, but the probability density function is more for statisticians. It has some very good properties, and of course, once you know CDF, you can get PDF by differentiating the CDF to get PDF, and similarly, if you have a PDF, you can always integrate it and get back CDF. So essentially, they're not two separate models. They are just looking at the random variable distribution in different ways. As far as hydrologic data analysis is concerned, CDF makes sense for us in a lot of applications. Okay. So with that, how do you obtain CDF and PDF? One approach is to use the sample data and use plotting position formulas. So here we use ranks and the number of data points to construct the CDF empirically, as I showed you in the last lecture. And of course, once you have that empirical CDF, you can differentiate it to obtain PDF if necessary. But this is rarely necessary in hydrologic analysis, since we're always interested in looking at some threshold and saying, what is the probability of finding something greater than that threshold or being less than that threshold? We are seldom interested in a value taking an exact, in some exact value. So advantages of empirical plotting position formulas is they're easy to construct. You may even do it on a spreadsheet. It's easy to understand and they're intuitive, so that makes sense. They account for the fact that the sample is only a subset of the data. So most of these plotting positions account for the fact that your sample is not be all and all. That there is a possibility that you might see values over and above or less than what you've seen in that sample. The problem, however, is that that while that acknowledgement is made, you really cannot extrapolate outside the range, and and also the curve has no direct mathematical formula, so you cannot manipulate it easily. So you have to do some interpolation, and to back out numbers, intermediate values. Theoretical distributions. Theoretical distributions are mathematical functions that follow the rules of probability. So it can be any algebraic function, as long as if I integrate the PDF curve, it should equal 1. And the cumulative distribution function should be such that your y-axis can only go between 0 and 1 for the range of x values that the random variable can take. So as long as these probabilities are being met, as long as these conditions are being met, any algebraic function can serve as a PDF or a CDF. And what PDFs and CDFs typically do is they use 2 or 3 parameters to represent the population. Okay, so these are called population mean, population standard deviation, or more rigorously in statistics, they use the scale or location for mean, and then the shape or weight for standard deviation. And sometimes we might use a higher order moment like skewness or kurtosis to better get the shape, or to model the distribution, to model the shape of the distribution. There are many theoretical distributions related to processes that generate the data. For example, if you have mixing in your system, or there is some dispersion in your system, log normal distributions, arise from that process or from that mixing process. So a lot of times chemical concentrations in water are modeled using log normal distribution. Similarly, Poisson distribution can be used to model arrival rates of independent events. So if I have a whole bunch of rain events or rainfall events happening, one independent of the other, then I can use a Poisson model in that case. So the one other advantage of using a theoretical distribution is the theoretical distribution is not limited to your sample size, and you can actually find values outside the range of the sample. So you can actually, extend your sample over a large finite domain, as long as the conditions in which you collected the samples hold true outside that range as well. So the probability models, random variables are characterized using probability distribution functions. There are hundreds of probability distribution functions. The 3 books that I show here, particularly Koltz et al., and Koltz, Johnson, and Balakrishnan for continuous univariate distributions, and then Johnson, Kemp, and Coates for discrete distributions are books that document like hundreds of distributions. And the key issue, regardless of what distribution you use, the probability models are always for the population. So again, as I said, we know everything there is to be known about the sample, but we do use the sample information to calculate or estimate the parameters for those probability models. Okay. While there are many probability distributions, a handful of those are used in hydrology. You can get by knowing a handful of distributions. So I'm going to go over and talk about a few important distributions in hydrology and where we use them in our hydrologic analysis and design. Okay. So I'll start off with discrete distributions. Discrete distribution basically means that your random variable takes a finite number of values. So for example, if I look at flood events, I can have no flood events, 1 flood event, 2 flood events, 3 flood events in a given year. I cannot have a 2.5 flood event or a 3.5 flood event. So this is a discrete random variable. Okay, so if I have a discrete random variable, the PDF is actually called the probability mass function, and the PDF, as I said before, measures the likelihood. In this case, the PDF actually measures the probability. So not only it measures the likelihood of which value is most likely, you will also actually get the probability in case of discrete distribution. So again, the probability in this case is relative frequency, and if I look here for this data set, I can say that 3 flood events a year is very likely. However, I could have 5 flood events, 4, or sometimes it may not flood at all in that stream. Okay, so and then the cumulative mass function essentially adds, so the 0 remains the same. For 1, I add whatever the probability 0.2 plus the probability of 0, and that gives me 1. I add these two to get, and all these three to get that value, add this four to get that, add these four to get that value, so on and so forth. So this is what we learned when we first learned probability in our grade school or high school. These are the types of distributions that we learned. Like, we count, bin, create a histogram. The histogram or the relative frequency histogram gives us the probabilities, and then the cumulative frequency histogram gives us what is known as, the cumulative mass function or the cumulative density function. Okay. The key point to remember is the discrete random variables only take finite sets of values, the binary state variables or multi-state variables. Okay. The empirical PMF and CMF can be constructed using histograms, as I said. So very easy to construct them empirically. You don't have to have a plotting position formula in case of discrete distributions, but in case of continuous distributions, you do need a plotting position formula. Theoretical distribution functions. The binomial distribution and Poisson distribution are the two distributions I'm going to talk about in this class. Binomial distribution is when you have two states, and then the Poisson distribution when you have a number of events occurring during a period of time. Okay, so you could also have a multinomial distribution where you have multiple number of states you can take. So the rolling of the die is a very common example in statistics of multinomial distributions, because the die can take one of the 6 possible states. The binomial distribution, that commonly, you talk about, flipping coins. First thing that comes to mind when we talk about probability is coin flips or rolling of a die, and those are your binomial multinomial distributions. And I talked about Poisson a little bit, talked about number of events that are happening, like number of rainfall events that are happening, that would happen in a year at any given location. So binomial distribution, the probability mass function for binomial distribution is given by this. This, you may recall, is a combination function. So basically it's saying if I look at n number of events, the total events is n, what is the likelihood of getting X events to do something? Okay, so X successes out of n possible events, and P is that probability of success. So there are 3 parameters. N is the total number of events. X is the number of events where you've had success or you want success, and then P is the probability of success. When we say success, the success can also be a catastrophic event in case of hydrology. So, for example, we could look and say, well, if I have the probability of a drought is like, say, 5% or 10%, what is the probability that I'll have 3 drought years in a period of 10 years? In a decade, 3 years of the decade are going to be drought, and you can estimate that using the cumulative probability, just using the probability mass function of the binomial distribution. If I want to say, well, what is the probability that I will see no more than 3 years of drought, then that would mean I could have 0 years of drought, I could have 1 year of drought, 2 years of drought, or 3 years of drought. Okay, so if I have 4, I know it's more than 3, so it's no longer less than 3. So in that case, I sum up for various values of I goes from 0 to 3, and then I use the combination function, the probability, and use these calculations. Again, you can make these calculations in Excel using combin function, or R gives you functions to get binomial distributions. So I'm going to show that in the next class on how do we calculate this. But for now, some of the hydrologic examples are, what is the probability of a drought? So we can define 2 states. One state is when your system is under drought, and then the other state is when the system is not under drought. Similarly, for a more environmental example, the probability of water being contaminated. So either you have contaminated water, or you have water that's not contaminated. You can't have them both at once, so that's a binary state. So just a small illustrative example, a historical analysis of rainfall data indicated that below average rainfall, which is an indicator of drought, was noted 20% of the time. So if you look at 100 years worth of data, rainfall data, take the average and then check every year and say, hey, what was this year's rainfall greater than the average, in which case there's no drought, or less than the average, in which case there was a drought? What we found was 20% of the times there was less than than the average, which means there was drought. What is the probability that there will be exactly 3 years of drought in the next 5 years? So in this case, our n is 5, our x is 3, and then the probability is 0.2 or 20%. So when I plug into this equation, I get about 0.0512. So the probability of seeing 3 drought events in 5 years is 0.0512. This is not telling when those drought events can happen. They can happen first year, second year, third year, or they can happen like second year, fourth year, and fifth year in various permutations or combinations. But we are not going to see more than 3 droughts in 5 years. Okay. What's typically more interesting to us, or what we typically want to see in hydrology, is what is the probability that there will be no more than 3 years of drought in the next 5 years. So in that case, we could have 0, which is no droughts, and then 1 drought, 2 droughts, or 3 droughts. So no more than 3 years of drought means you cannot have 4 years of drought or 5 years of drought, but you can have 0 years of drought, or 1 year of drought, 2 years of drought, or 3 years of drought. So here again, my x is 3, p is 0.2, n is 5, but I goes from 0, 1, 2, 3, and if I do that, I get a value of 0.9933. So there is a greater than 99% chance that there won't be more than 3 years of drought. So the probability of getting 4 years or 5 years of drought is fairly small. Poisson distribution, it's a discrete distribution used to represent the number of independent events within a fixed time. The number of independent rainfall events within a year, for example. So we're not talking about rainy days. So you can have an event that lasts for like 2 or 3 days, and then it won't rain for a while. Then you might have another event. So we're talking about those events that could span multiple days, but we count them as one rainfall event. That is all part of the one rainfall event. So there could be some lull in that rainfall, but still it could be part of that. We could still call it the rainfall event. A closely related continuous distribution is the exponential distribution, which says what is the time between those rainfall events. So the Poisson distribution assumes stationarity, and it says that the rate at which that events occur is constant. And we represent the average number of events per interval using lambda, and k is the events that we are interested in a given interval. So these are the formulas for the probability mass function and the probability distribution functions. Poisson distribution is what we call a single parameter model because we represent the distribution using lambda, one parameter lambda, which is the average number of events per interval. So if I go back and show you a quick illustrative example, the average number of rainy days in a year at a given location is 45 days. What is the probability that a given year will have 30 rainy days? So so my k is 45. So on average, there are 45 rainy days. It doesn't mean that every year will have 45. Some years will have 0. Some years will have 100. So if I take an average over a very long period of time, I get my lambda for the Poisson distribution, and then k is 30 days in this case. So I plug in k and 45 and 20 and 45 and get the probability mass function to be with the value to be 0.0043. So basically it says that the probability that any given day will have, a year will have 30 days of rainy days is 0.0043. What is the probability that a given year will have more than 100 rainy days? Then I use the cumulative mass function, but again, I'm interested in more than. What cumulative mass function tells me is less than. So I do 1 minus CMF for the 1 minus cumulative mass function and use first the mass function with k equals 45, and then my I goes from essentially 1 to 100. And that gives me, actually it goes from 0 to 100, and that gives me the total number of rainy days. So 100 in the second case. So we use the probability mass function or the cumulative mass function, and then we do 1 minus because we're interested in greater than rather than less than. So again, that is a very, very small probability. So this is generally, if it's having on an average 45 days of rainfall, that's a fairly dry place, a semi-arid or an arid region. So expecting 100 days of rainfall there is perhaps wishful thinking, and that's what this probability tells us. Continuous distributions, well, uh, most of the variables that we use in hydrology vary continuously, and continuous variables have some special characteristics. Sometimes they can only assume positive values. So if I look at a stream flow over a year, it can never have a negative value. Rainfall over a year, same thing. And sometimes they can only assume positive values greater than zero. So if we say rainfall, one could theoretically argue that it has to have a finite amount of water. So if there was no rain, that's zero. So theoretically, one could argue and say that rainfall implies that there is a value greater than zero associated with the water that's falling from the atmosphere. So similarly, stream flow, you can argue the same thing. If there is flow, there has to be water. The flow rate should be greater than 0 CFS. So and then there are times when a variable can assume both positive and negative values. Temperature in Celsius or in Fahrenheit scale is an example of that. Temperature in Kelvin scale obviously can only take positive values. So again, there are hundreds of continuous univariate distributions, or these are mathematical functions that satisfy the laws of probability. But again, we are interested in a handful of those in hydrology. In particular, the most famous distribution of all is the normal distribution, and the normal distribution is defined using two parameters, namely the mean and the standard deviation. And it's by convention that we always use Greek letters mu and sigma to represent mean and standard deviation of the population. Again, we are looking at these random variables to represent the population, not the sample. We might use sample mean and standard deviation to estimate our population mean and population standard deviation, but again, our interest always is in the population, in describing the population. The normal distribution leads to a symmetric distribution, and if you have multiple additive processes, that typically follows normal distribution. So porosity is an example of a random variable that we typically associate with normal distribution. Groundwater levels is another parameter where normal distribution has been used, because it's addition of water coming from various pores into the well. So so it's an additive process. The log normal distribution is similar to normal distribution, except that we say that the log of the random variable x. So if x is our variable and we take logs, that log follows normal distribution. So the formula is about this formula is applied for both normal and log normal. However, this x has to be log transformed first to get your log normal distribution. So obviously you can't take log of a negative number, so it does not work with negative data. And then the log normal distribution represents multiplicative process instead of an additive process, because if I take a times b times c and take the logs, then it becomes log a plus log b plus log c. So it's actually a multiplicative process, and so mixing is a multiplicative process. So if there is dispersion or concentrations, are very typically follow log normal distribution. Log normal distribution also has this character that you can't have negative numbers. So and that again is very characteristic of our concentrations and flow rates. So log normal and normal distributions are best suited to represent central tendencies. They're not really distributions used to model extreme values in most cases. Gamma distribution. The gamma distribution is really the workhorse distribution in hydrology. Basically, what gamma does is, these are some complicated formulas. It uses the gamma function and the incomplete gamma function to describe our probability distribution functions. Gamma and incomplete gamma are what we call special functions. They have certain special properties, and you most likely need a computer to calculate this gamma and incomplete gamma. Nonetheless, if you look at the random variables and I use different k and theta, the two parameters, the shape parameter and the scale parameter, I can get various types of curves. So that's how we can generate a wide range of distributions using gamma distributions. In hydrology, we also refer to gamma distribution as a Pearson type 3 distribution. after the famous hydrologist Pearson, who popularized its use in hydrology. And but as you can see, one thing about gamma distribution is gamma distribution only works when x, the random variables, assume values greater than 0. If there is value equal to 0, gamma doesn't work. A very typical use of gamma distribution is to model rainfall or model the probability distribution of the amount of rain that happened on rainy days or the days when it rained. Of course, you can't model zeros, which are excluded. And then, if you say there are rainy days, some days you will have, 1 inch, some days you will have half an inch. And if we can fit a gamma distribution to that data. Exponential distribution again is related to Poisson distribution through this lambda. Remember, you saw this lambda in Poisson distribution, which is the average rate of arrival. And exponential distribution is commonly used as the curve indicates. It follows an exponential curve. The probability density or the likelihood is very high initially, and then it falls off exponentially. So the time between two rainstorm events is basically represented using exponential distribution. That's a hydrologic application. So we say that the rate at which rainfall events come is a Poisson distribution, and the time between those two rainfall events is represented using exponential distribution. So again, Poisson and exponential distribution functions are very closely related. People also model the duration of the rainfall a lot of times using exponential distribution, saying that the time between the arrival of the first pulse of rainfall and the last pulse of rainfall, the time between them, if they are Poisson, then the time between those rainfall events are exponentially distributed. As I said, in hydrology, we are always interested in extreme values, either higher extreme values for floods, lower extreme values for droughts. So there are special distribution functions or special probability density functions that have been designed to capture this type of data, extreme value data. Again, normal distribution or log normal distribution may not work very well because they model the average tendencies, or they're very good at modeling mean behavior, but they're not very good at modeling the extreme value behavior. So these distributions can be categorized into three basic types: Gumbel, which is a 2-parameter distribution; Friche, which is used for precipitation and stream flow; and then Weibull, which is typically used for modeling extreme temperatures. So I show you the equations for the cumulative distribution functions for Gumbel, Friche, and Weibull. Again, they have 2 or 3 parameters: the location parameters, the scale parameter, and the shape parameter. So these parameters are estimated from the data that you have, a bunch of floods that have taken over time, a bunch of droughts, but these kind of tell us the probability of a drought less than certain magnitude happening, or probability of a flood, defined using some threshold stream flow happening, can be modeled using these extreme value distributions. There is all these types of distributions can be captured using what's called as a generalized extreme value distribution, or GEV, and mu is the location parameter, sigma is the scale parameter, and then you also have a shape parameter. So if we put that shape parameter equal to 0, you get Gumbel distribution, and if it's greater than 0, then you get heavy tail distribution. And so you can model various types of phenomenon with this 3-parameter generalized extreme value model. Again, this is f of x, which means, again, we're looking at cumulative distributions. So to summarize, hydrological variables can be continuous or discrete. A theoretical PDF and CDF allow us to model these random variables. Really, PDF and CDF are not two different functions. For a given distribution, you will have a PDF and a CDF. Okay, and you can either differentiate the CDF to get PDF or integrate the PDF to get a CDF. So they're one and the same. The theoretical distributions allows for modeling the random variable using 2 or 3 parameters, and we get these parameters using sample data. The distribution is always for population and not sample. The sample is used to model the distribution. We saw some common discrete distributions, or your binomial distribution, which is a yay or nay, binary type of random variable, the random variable that can only take two states, and then Poisson distribution, which can take multiple states, looking at arrival times. Okay, common continuous distributions, we talked about normal, log normal, gamma, and exponential, and I also introduced you to the Gumbel distribution, the Weibull distribution, and the generalized, the Fréchet, and the generalized extreme value distributions, which are used to look at extreme events like floods and droughts or very high temperatures in our system. So what we'll do in the next class is we will take some real world data sets and try to estimate parameters, or try to say how do we get these distributions, and then how can we use these distributions in hydrologic analysis. So that will be our next class. Until then, I suggest that you go back and review this material and review probability and concepts that you learned in your class, in your statistics class, or even in your undergraduate hydrology, so that you come prepared for our next class. With that, that's all I have for this lecture, and I hope to see you in class next week.